Hi, welcome to Dissolve Chemistry. Let us continue our discussion on this ionic equilibrium. In the previous video, we have discussed regarding ionization constant, ionic product of water, and then we have discussed how the pH scale is used to measure the hydrogen ion concentration. Okay, so in the present video, we will see a very important aspect, that is the dissociation constant of weak acid, dissociation constant of weak base, and the relationship between these two constants we will see. Okay, so you see here, suppose if you take a strong acid, now if you dissolve such as, you can take HCl as an example. If you dissolve that in water, what it will do? So it will ionize as 3O plus, you will be having plus Cl minus aqueous when you dissolve this in water, and your identity as HCl is being completely lost upon addition in water. Meaning is what? It is completely ionized, and you will be finding only in the form of S3O plus and Cl minus. So therefore, if I say that what is the pH of 2 molar HCl solution, if I say, so directly we will substitute that in what? This pH equation. So the H plus ion concentration directly we will take. I have given the value as 2 molar HCl, but you are taking that as a concentration of H plus ion. What is the reason for that? Because so 2 molar HCl in water, it will be in the form of 2 moles of H plus ion, means it will not remain as HCl, it will completely dissociate in water and it will remain as H plus. So therefore we will directly take it as pH is equal to minus log of 2. But same thing when you apply to weak acid, like acetic acid, if you take, so this acetic acid, when you dissolve in water, okay, suppose you have taken 1 mole of acetic acid, okay, in that only how much it is being dissociating? Only almost less than 5% is in the dissociated form in water, okay, aqueous. Now suppose if you want to calculate the pH of this, then how to do that one? Okay, so because most of the acetic acid in water, aqueous medium I am talking, okay, so in water, actually what it is remaining? So it is remaining in the form of acetic acid only. Okay, so as it is remaining as acetic acid and only part of that is being ionized, then if you calculate its pH by taking as 1 molar, then what happens? It will not correspond to the true pH of the solution. Okay, you should remember that. So therefore we have to go in a different way, or we have to approach it in a different way, we can say. So how much amount of the acetic acid is remaining in the dissociated form? Okay, and always remember, it establishes an equilibrium, and that equilibrium is dynamic, and we have taken this as one of the important ionic equilibrium. So as it is dynamic equilibrium, but equilibrium concentration are remaining constant, so therefore we can give the equilibrium constant for this equation, and then we will try to calculate the things. Okay, so for this reason we will see the ionization constant, which is very important for weak acid, and ionization constant similarly for weak base is also very important to calculate the pH or pOH, whatever it is, to tell the concentration of the number of H plus ions or number of OH minus ion and all that. Okay, so we will see in detail with that. First we will talk about dissociation or ionization constant of weak acid. Okay, so first we will approach with the taking general example. Dissociation constant of weak acid. So let us consider a weak acid HA. Okay, it's a weak acid you consider. Now when you take this HA and if you dissolve it in water, now it will be acid, acting as acid, and this will be acting as base. Okay, so now what happens? So it will establish an equilibrium. H3O plus aqueous plus A minus aqueous. Okay, so that is how it is undergoing dissociation in water. Okay, now the thing is, as it establishes an equilibrium, okay, so therefore let us express that the equilibrium constant for this. Okay, so when you express that equilibrium constant, then what you will be finding, that H3O plus into A minus divided by HA, okay, and H2O. And we know that water is present in the large quantity when compared to acetic acid, so therefore it will be taken as constant. So therefore capital K into, okay, so we will write one other step, plus into A minus divided by HA into small k, and that small k if you take out here, and then the k into small k, which is equal to H3O plus A minus divided by HA. And these two put together we call it as what? Ka, dissociation constant of acid, and it is given as H3O plus into A minus divided by HA. Okay, so now this is called as what? Ionization constant or dissociation constant of weak acid. Why it is constant? You should remember that the concentration of H plus and A minus at equilibrium will remain constant, okay, at a given temperature, and even of a acid also, undissociated form of acid is also going to remain constant. Now once you know the value of Ka, then you can tell the strength of an acid, means how much strong it is. What is the strength of the acid means? Strength of the acid means how much amount of the acid will undergo dissociation to give H plus ion. More number of H plus ion gives, then we call it a strong acid. Strength is high, we call. If it is giving less number of H plus ions, we call it as weak acid, we call, right? So therefore, to express the strength, how we are going to express? If the Ka value is high, itself indicates that, because only it is possible when the values of this H plus and A minus, means which are in the numerator, if its value is high, so then obviously our Ka value will be high, or its value is low, then in the denominator Ha value will be high, so therefore your Ka value will go down, right? So therefore the strength of the acid can be expressed in terms of dissociation constant. Okay, so now to what extent the weak acid has undergone ionization, okay, or we call it as what? Degree of dissociation or degree of ionization. Okay, so let us find that one. Okay, let us consider the same equation. Now initial concentration. Initially your Ha will be what? C is the concentration, and you take these two as 0, 0. Okay, so let us take it as 0. So now after time interval, or when it attains an equilibrium, okay, at equilibrium, then the concentration of H plus, we will take it as C alpha, and concentration of A minus, we will take it as what? C alpha. So therefore your concentration remaining, Ha concentration remaining at equilibrium will be what? C minus. C alpha amount is going to be dissociating, means what? So initial concentration is this, and C alpha has gone or dissociated, then at equilibrium amount of Ha will be C minus C alpha. Okay, So C represents the concentration of H plus ion into alpha is going to represent degree of dissociation, means to what extent it has been ionized. Fine. So this is what we are going to get at equilibrium. Now what you do, you substitute these values in your Ke, okay, dissociation constant of acid. So you substitute the values, okay, into the equation. So therefore C into alpha, C alpha, okay. So why we have taken this? Because we know that, or if you are not remembering, we will write this, right? Fine. Ka is equal to what? What is your equation? Ka is equal to H plus A minus divided by HA. Okay. So now which is equal to H plus is what? C alpha. H plus or S3O plus. Both are one at the same. Don't worry. C alpha and A minus is again, it is also C alpha divided by C minus C alpha. Okay, this can also be written as what? We will write like this, C alpha into C alpha divided by C, we will take it common and you will be getting 1 minus alpha. So therefore 1C will get cancelled. Then what remains? In the numerator, you will be getting what? In the numerator, so we will be having Ka is equal to C alpha square divided by, and in the denominator 1 minus alpha. Okay. Now, let us define the term where C is the concentration of the acid, and alpha is degree of dissociation or ionization. Degree of dissociation. Now, as we have said, it is a weak acid, then this alpha in the denominator, okay, it is very small because degree of dissociation is very small amount. So therefore small amount means, so 1 minus alpha we will take it as approximately equals to 0, or it whole term we will take it as unity. So therefore your Ka is equal to C alpha square. Okay. So now what is this degree of dissociation? Alpha is equal to, we will write alpha square is equal to Ka by C, and alpha is equal to under root Ka by C. So this is very, very important. Okay, if you know the initial concentration of the acid, and if you know the ionization constant or dissociation constant of that acid, then you can calculate the degree of dissociation of acid. Once you know the degree of dissociation, then you can tell the concentration of the H plus ions or OH minus ions, H plus ions. Okay, once you know the concentration of H plus ions, then you can determine the pH of a weak acid also. Okay, as I have said, that directly by taking into the concentration of the weak acid, we cannot calculate the pH as we can do with the strong acid like HCl. Okay, directly whatever the concentration of the HCl is given, directly we will put it into the pH equation and then we will get the pH value. Okay, whereas for weak acid we cannot do like that because we don't know the concentration of the H plus ions. Okay, because to what extent it is ionizing we don't know. When we are not knowing ionizing, to what extent H plus is present, because it is undergoing partial ionization. So therefore we have to approach like this. So therefore alpha is equal to under root Ka by C. So therefore if you know the dissociation constant, if you know the concentration, we can calculate alpha. Once you know the alpha, and then how to calculate the concentration of H plus ion. So we know that the concentration of H plus ion is equal to what? C into alpha. So where C is what? Concentration of acid. How much acid is being taken? So that is what. And alpha is what? Degree of dissociation. Okay. So initial concentration of the acid and dissociation constant, these two things if we know, then we can degree of dissociation, then followed by we can calculate hydrogen ion concentration. Once you know the hydrogen ion concentration, then we know that pH of the solution can be easily found. Okay, we can determine that one. Okay, this is how the dissociation constant Ka of weak acid, that is Ka, plays a very important role, or it is very important to tell the concentration or strength of a weak acid. Okay, strength in terms of Ka directly we can say, or in terms of degree of dissociation we can say, or we can calculate H plus ion concentration also, and we can calculate further pH of the solution also. Okay, so that is all about dissociation constant of weak acid. Now let us look into dissociation constant of weak base. Students, please remember, both are one at the same, formulas are same, small variation is there, so that we will see. Well, as we have seen for strong acid and weak acid, how we have compared, similarly, when you compare a 1 molar NaOH, okay, so now 1 molar NaOH, 1 molar ammonia, if you want to compare their strengths, okay, or to what extent they are going to behave like base, of course directly we can substitute this and we can calculate its pOH, or we can calculate pH. Okay, so because the hydroxyl ion concentration, okay, of OH in aqueous medium, in water, okay, so it corresponds to the same concentration of a NaOH what it is being prescribed. But similarly for ammonia, when you dissolve this in water, so you will be having what? Ammonium cation plus OH minus ion. So the concentration of OH minus ion, okay, will not correspond to what it is being specified as the concentration of the base. Okay, why? Because it is partially dissociating. Okay, completely it is not what accepting the proton, isn't it? So in such situation, so again we have to rely on dissociation constant of base. Okay, so let us see that one. So let us take, we will take what? A general example, BOH. Okay, when you dissolve this in water, it undergoes partial ionization to give B minus aqueous, okay, plus OH minus aqueous. That is B plus aqueous and OH minus aqueous. Okay, so now what you do is you apply, as it is attaining an equilibrium and this equilibrium is dynamic. Okay, and so if you apply the equilibrium constant, okay, therefore what you will be getting? B plus OH minus, okay, divided by BOH and H2O. Okay, so therefore you take it as constant, so therefore equilibrium constant K into small k, which is equal to B plus OH minus divided by BOH. Okay, and this turns out to be Kb. Okay, so this Kb is equal to B plus OH minus divided by BOH, molar concentration of what? Weak base. Okay, so now what we will do is, so this is what we call it as what? Dissociation constant of weak base. Okay, it is exactly same as that of your weak acid, we can say. And similarly, we will find degree of dissociation of base. So now, for the same equation, you can apply The initial concentration, you take it as C and it will be 0, 0 and at equilibrium. So you find this as C minus C alpha and B plus and OH minus. Zero, zero. Here you can take C alpha, C alpha. Okay. So now at equilibrium, these are the concentration, means directly you can substitute this in the equilibrium or dissociation constant equation. So therefore, Kb is equal to, you will be having C alpha into C alpha divided by C into 1 minus alpha. So therefore, C, 1C will get cancelled. So therefore, it turns out to be C alpha square divided by 1 minus alpha. Okay. So that is what is your Kb is equal to, you will be getting dissociation constant in terms of degree of dissociation. So therefore, alpha is equal to under root Kb by what? You will be getting C. Okay. So as in the denominator, once again, same alpha, we are going to neglect it because it is a weak base. The degree of ionization will be very minimum. So therefore, it will be taken as unity in the denominator. So therefore, then it turns out to be, this is what is the equation that we get. Similarly, here also we can calculate degree from the dissociation constant of weak base. And if you know the initial concentration, we can calculate degree of dissociation. Once you calculate the degree of dissociation, you can check the concentration of the OH minus ion, okay, by using that is C alpha, okay. So C alpha initial concentration, degree of dissociation, then it will tell you the concentration of OH minus ion at equilibrium. Once you know the concentration of the OH minus ion, you can calculate pH, pOH, okay, all that one, okay. And you can measure the strength base, okay, by using Kb value. Higher the Kb value, then stronger will be the base we call. Lower the Kb value, then we call it as weaker the base we call. Because the dissociated forms are on the numerator and undissociated form is in the denominator of the equation. Okay, I hope you have understood the meaning of this. Now we will see the relationship between K and Kb, which is very interesting. Okay. Relation between Ka and Kb. So which is very interesting. Okay. So we'll go in detail with this. Okay. So now a strength of any acid or base, it depends according to Bronsted and Lowry. Okay, we will write one example, then it will be easier for us. Say for example, ammonia you have taken, and if you dissolve this in water, so then your ammonia will be base and your water will be what? Acid. Okay, so now what happens? It will undergo partial ionization or dissociation we call. So then you will be getting what? Ammonium cation plus OH minus ion, aqueous. So also aqueous, you write. So here what it is called as conjugate acid, and it is called as what? Conjugate base. Okay, when you look into this equation, so now ammonia is base, it accepts the proton from water, where water is acting as acid and it is donating the H plus ion. Okay, so now after that what happens? It forms ammonium cation and it has got with what? One additional H plus ion. So therefore readily it can give back to the OH minus ion. As it gives back to the OH minus ion, means it is going to act as what? Conjugate acid. So as it is acting as conjugate acid, means it must have certain tendency to give back that proton. It may act as a what? We call it as acid. Okay. So therefore it is going to act as acid, and whereas it is the acting as a conjugate base. Okay. So now the strength of this acid, okay, to give back the proton, right? So we will consider that directly. So we'll take this one like this. NH4 plus aqueous, it is an acid which is going to give an proton to the water, you can consider. Okay, so there what it will be? NH3, right, plus H3O plus you will be having aqueous. Okay, this is also aqueous we will take. Write the equilibrium constant. This is what? Kb is equal to what you will be having? NH4 plus, okay, into OH minus, right, divided by what you will be taking? Only concentration of NH3 we will consider. Fine. So which is then Ka is equal to, for this equation as it is the dissociation of acid it involves. So therefore Ka is equal to NH3 and S3O plus. Okay. So divided by what you will be having? NH4 plus. Now what you do is at equilibrium back the proton and getting converted into NH3, okay, and NH3 accepting the proton to give this ammonium cation are equal. So therefore these two constants should be equal at equilibrium, okay, or we are going to get the product of that will be what addition we can get, right? So therefore a new constant K which is equal to Ka into Kb. Substitute these values. NH4 plus into OH minus divided by what you will be having? NH3, okay, into, right, NH3 S3O plus divided by what you will be having? NH4 plus. So now these two will get cancelled, this will get cancelled, this will also get cancelled. So therefore the product of Ka into Kb, okay, will be equals to H3O plus and OH minus, or we can write as H plus and OH minus. This is nothing but what? The ionic product of the water, that is your Kw. Okay, literally if you substitute the value of the dissociation constant of these two, okay, so then definitely we'll be getting what? 10 to the power minus 40. Okay, so that is how you get. So therefore always remember the ionic the product of Ka and Kb means dissociation constant of weak acid and dissociation constant of weak base will be always equals to what? The ionic product of water. Okay, 10 to the power minus 40. Okay, so this is how we are going to bring the relationship between Ka and Kb. Okay, I hope you have understood. So if you have any doubts, please write in the comment box. Okay, and don't forget to subscribe our channel. Thank you for watching. Thank you.